In this video, we're going to look at the scalar equation of a plane in space. So consider a plane with a given normal vector n. So here's our plane, here's our normal vector n. The normal vector will define the direction of the plane, but not the position. So that means that the normal vector can give you like where the plane or how the plane is oriented in 3D space, but not exactly where it is exactly anchored in 3D space. So its exact location in 3D space. It just gives like the orientation of a plane in 3D space. However, if you also have a point, P naught, on the plane, you can then say, okay, well, the plane exists in this exact location. You have both the orientation of the plane in 3D space and its exact location. So you're going to do this using a similar method to writing the scalar equation of a line. Find the scalar equation of a plane, which is perpendicular to this normal, 5, -1, -6, and contains the point 2, -3, and 4. Okay, so what we're going to do here is I'm just going to hand sketch another point, right? It says right here, let P, I'll highlight it for you right here. Let P, X, Y, Z be any point on the plane. Okay, so I know that this point right here, P naught, is equal to 2, -3, and 4. And then this point right here is any other point on the plane right there. So this is some other point, and then I can just write X, Y, and Z. Well, what you might see here is that the normal vector is perpendicular to this vector P naught P. So what we will say is the first thing that we're going to do is we're going to create the vector P naught P, right? And so we say final minus initial, so X -2, Y -3, and Z -4, okay? So that right there is equal to X -2, Y +3, Z -4. And then the normal vector we already have defined as 5, -1, -6. So we can state, therefore, that P naught P dot product the normal vector, right, because they're perpendicular, has to equal to 0. And so therefore we can say that X -2, Y +3, Z -4, dot product 5, -1, -6 is equal to 0. So then I can just say X -2, -1, Y +3, -6, Z -4 is equal to 0. Simplifying this entire thing, so distributing and simplifying, what I get is 5x minus y minus 6z plus 11. So expand, collect like terms, simplify, equals to 0. And you'll note that that looks a lot similar to this right here. ax plus by plus cz plus d equals 0, and that is your scalar equation of the plane. So here, this equation right here will generate x, y, and z coordinates for any point that sits on the plane. Now what we'll do is we'll define it we'll derive it in general terms. So find the scalar equation of the plane, which is perpendicular to n, ABC, and contains point P naught, X naught, Y naught, Z naught. Let P, X, Y, Z be any point in the plane. P naught P is in the plane, so P naught P dot the n vector, the normal vector, should be equal to 0. Okay, so we know that P naught P is the final position vector minus the initial position vector right there. So that's just going to be equal to x minus x naught, y minus y naught, and z minus z naught. Okay, the normal vector is given as a, b, c. Okay, so then we have P naught P dot the normal vector is equal to x minus x naught, y minus y naught, and z minus z naught. all dot product with ABC. Okay, so we perform our dot product operation. Okay, this is also equal to 0, right? So our dot product operation should say that A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught is equal to 0. So I have AX plus BY plus CZ, and now I'm going to collect all my AX naughts, BY naughts, and CZ naughts. So minus AX naught minus BY naught minus CZ naught is equal to 0. All of this right here equals my D term. So therefore, AX plus BY plus CZ plus D is equal to 0. And you can see that these right here are components of the normal vector. So I can just write that, components of the normal vector to the plane. Okay, so the scalar equation of the plane is given by AX plus BY plus CZ plus D, where the plane has a normal vector ABC, and A cross B is the normal vector. So the cross product of two non-parallel vectors in the plane is the vector normal to the plane. Okay, find the scalar equation of OP, and then it gives you the equation of a plane in vector form. Well, I can immediately see that this is A and that this is B, and I can define the normal vector as A cross B. So the normal vector is simply A cross B, okay? And then I also have a point on the plane. So I have a normal, and now I need a point on the plane. Well, that's just 7, -2, and 3. Okay, so that my normal vectors should be my cross product of A and B. So 1, 2, -4, cross product with -3, 5, and 1. And that is equal to 22, 11, and 11. Now I can reduce that to 2, 1, 1, which I can use. This is still normal to the plane, right? I'll say still normal to the plane, but has reduced magnitude. Well, the magnitude doesn't matter. It's irrelevant, right? All we wanted was a vector that's normal to the plane. So I look at my components 2, 1, and 1, and so I can say, therefore, 2x plus y plus z plus some constant d is equal to 0 based on my definition for the scalar equation of the plane. I sub in the point, 7, -2, and 3. So 2 times 7 minus 2 plus 3 plus d is equal to 0. And I find that my d is equal to -15. So, therefore, 2x plus y plus z minus 15 is equal to 0. That's the scalar equation of my plane. All right. Find the scalar equation of the plane containing the points 2, 3, -1, q, -4, 1, 2, and r, 1, 5, -2. You can draw yourself a plane right here, and the reason why I did that is I want to show how we're going to approach this. Well, remember that you define a plane with 3 points. We said that. I'm just going to scroll up and show you where we have that in our notes. Here. This is on page, looks like on page 15, it says 3 points are required to define a plane. All right, so so we're going to have find the scalar equation of the plane containing these 3 points. So I'll just put P over here, Q over here, and R over here. So I've got my 3 points. And look, I can actually make basis vectors A and B from those points. So I can say A is equal to PQ and B is equal to PR. Okay, so And then n, the normal vector, would simply be equal to A cross B, or PQ cross PR. Okay, so let's find what vector A is, okay? And so A is PQ, so that means I'm going to take, sorry, PQ right here, so I'm going to take -4 minus 2, okay, and I get my PQ, so therefore PQ, -4 minus 2, -6, 1 minus 3, -2, 2 minus 1, +3. PR now. PR would be 1 minus 2, that's -1 right there. Sorry, let me make a better bracket here. Okay, 5 minus 3, that's 2, -2 minus 1, and that is equal to -1. Okay, so n is just, like I said, is the cross product of PQ and PR. So go ahead and perform that cross product operation, and what you should find is that you get -4, -9, and then -14. Okay, well, what we can do is we can just factor out a -1 and write 4, 9, and 14. And even though this vector right here, this one is heading in the opposite direction, well, even if it's heading in the opposite direction, so like for example, this right here is my cross product, and that we've defined as -4, -9, -14, right? But what I can do is I can multiply this entire thing by -1, and I'll still get a vector that's perpendicular, right? So I can still use as a normal vector, right? It's still 90 degrees. It's just literally in the opposite direction, right? Okay, so what I'll do right there is I'll say, okay, therefore, use these components, 4x plus 9y plus 14 plus d is equal to 0. I sub in a point. And in this case right here, I'll just sub in the first point that's given to me, 2, 3, -1. So 4 times 2 plus 3 times 9, right? 9 times 3 plus, I'm not really, sorry, 14z, apologies. 14 times -1, right there, plus d is equal to 0. Okay, and so then d is equal to -21. Okay, so therefore, 4x plus 9y plus 14z minus 21 is equal to 0. Okay, so I'm going to insert a shape here. I'm going to put my box around it like I normally do, or like I have done, and there we go. Okay, yeah, so this one right here is the last example for this lesson. So find a vector equation for the plane x plus 4y minus 2z plus 8 is equal to 0. So we're starting with the scalar equation of a plane, and now we'll go backwards to the vector equation. So what I'm going to need to do is to find a vector equation of a plane, I need my basis vectors, right? So you can write this. I need my basis vectors a and b, okay? And then I need a point on the plane. Okay, so remember that you can make a plane if there are 3 points. If you have 3 points, you can make a plane. So I'm just going to make a plane right here, okay? And you'll see that I need 3 points, right? So I'll need like P, Q, and R. Okay, so I'll say P, Q, and R, right, to generate a plane. So PQ would then become my basis vector A, and PR would become my basis vector B. So how do I get 3 points on this plane? Well, literally, I can just use the scalar equation of the plane, okay? So I'll say for point P, I'm going to set y and z equal to 0, right? I can choose my values for y and z, and then this will generate the point, the x value that then lies on the plane. So I'll have right there x plus 4, 0 minus 2 times 0 plus 8 is equal to 0. So that means that x is equal to negative 8. So point P is defined as negative 8, 0, and 0. So we'll do the same thing for Q, except for Q, what I'm going to do is I'm going to set x equal to 0, and I'll set z equal to 0. Okay, so if x is equal to 0, then I have 0 plus 4y minus 2 times 0 plus 8 is equal to 0. And then I have y is equal to negative 2. Okay, so then Q is simply 0, negative 2, and 0. And then I have R as well, and R is set x is equal to 0 and y is equal to 0. All right, and so I'll have right here 0 plus 4 times 0 minus 2z plus 8 is equal to 0. So z therefore is equal to 4. And so r right here is 0, 0, 4. Okay, so I have now 3 points on the plane. So I'm going to make A equal to PQ. A is equal to PQ. So then A is simply equal to, so then 0 minus minus 8, that's 8. Negative 2 minus 0, that's negative 2. And 0 minus 0 is 0. Okay. B is going to be PR. Okay, so if B is PR, then that's simply equal to 0 minus minus 8. That's 8. 0 minus 0 is 0, and 4 minus 0 is 4. Okay, so I've got my two basis vectors, A and B. I have a point on the plane, which is negative 8, 0, 0. So therefore, OP is equal to negative 8, 0, 0 plus, and then we'll say S, 8, negative 2, 0 plus T, 8, 0, 4, where S and T are parameters that are elements of all real numbers. Okay, so let's finish this off. Summary equations of planes. To find the equation of plane, for a vector, you need 3 non-collinear points, or a point and 2 basis vectors. Again, those basis vectors are also non-collinear. Scalar, you need a point and a normal, okay? Or you could just have 3 points, and then you can create 2 vectors and a normal using cross product there. So that's something that we said, or we drew. If two planes are parallel, then that means that they have the same normal. If a line is in a plane, any point on the line is also in the plane, and the direction vector for a line is also a vector in the plane. All vectors parallel to a plane are also in that plane, right? So if a vector is parallel to the plane, you can just move it down and preserve its magnitude and direction, and it can still be in the plane. Now, if one plane is perpendicular to another, the normal vector for one is the basis vector for the other. If two planes are parallel, any vector in one plane is also a vector in the other, and a plane equation can look like a line equation if one of the components of the normal is 0. Okay, homework is listed right there. That's the final lesson of the unit. Thanks for watching.